One of the things that was really disappointing about this course is the fact that we're not, in this semester, going to talk about the electron transport chain, right? It ends with the Krebs cycle, which I think is frustrating. But I wanted to kind of just spend a little bit more time discussing the Krebs cycle and discussing the energetic effects that has on the cell as a whole. So over here we have the net reaction of the tricarboxylic acid cycle. Their net reaction to the Krebs cycle is 1 molecule of acetyl-CoA, 3 molecules of NAD+, 1 molecule of FAD, 1 molecule of ADP and inorganic phosphate, and then 2 molecules of water that are ultimately going to react to produce. This is going to react to yield 2 CO2, 3 NADH, FADH2, ATP, 2 H+, and then coenzyme A as our product. So these are all the things that we had mentioned, or that were mentioned in the reactions but weren't actually staying in the cycle, stuff that enters it and then stuff that leaves it. And some notes that I wanted to mention as well, or some notes that would need to be made, would be that NADH is a higher energy state. It is a more energetic molecule if you think about it than that of FADH. So NADH is going to generate ultimately 2.5 ATPs per 1 molecule of NADH at the electron. Whereas FADH2 only generates 1.5 ATPs at the electron transport chain. So the next thing that I wanted to mention would be the total energy per glucose. And since we're eukaryotes and we're not prokaryotes, we have the mitochondria and then the cytoplasm, and then 2 of these metabolic events are, I guess, happening in different locations. So we need to kind of look at each and every one of those individually and then add up the totals of each and every one of those. So for the cytoplasm, we only, I guess, metabolic event happening there is glycolysis. Glycolysis, in case you don't remember, gives us 2 ATP and then 2 molecules of NADH. Now, the issue with NADH is that it cannot be just directly transported as is to the mitochondria. So for reasons that aren't 100% clear to me, we got to transfer it, the NADH, to either FADH, FADH2, or transfer it to another NAD plus to give us NADH, which for me, like, just thinking about that, in terms of entropy, where you start off with a reactant of 2 coefficients and you end up with 2, like, that's 100% yield. Like, I would win a Nobel Prize if I could do that. But anyways, I'm sure it's far more biologically complex than that, but we don't really have time to go over it. So because of whether or not it be FADH2 or NADH, and we have 2 of that could either give us 2 molecules of FADH2, which would be 2 times 1.5, and then we could also have 2 molecules of NADH, which would be 2 times 2.5. The total ATP produced just from the metabolic reactions of the cytoplasm can be 2 plus 3 or 5, which means that we could either have 5 or 7 ATP being produced. So for the mitochondria, there's really just 2 places that we have. We have the pyruvate dehydrogenase complex, and then we have the Krebs cycle. We get 2 NADH from the pyruvate dehydrogenase complex, and then the Krebs cycle gives us 6 molecules of NADH, 2 molecules of FADH2, and then 2 molecules of GTP, because what we're doing is, or ATP as well, because what we're doing is this, or what we're seeing up here, this is the net reaction per cycle per Krebs cycle, but this is happening twice per glucose molecule. So essentially, if you wanted to think of this in terms of per glucose, you just multiply this whole equation by 2. So when we consider the fact that we have 8 total molecules of NADH, we're going to multiply that by 2.5, because that's how much ATP we're going to get at the electron transport chain, and then 2 of FADH, and then 2 of the ATP that we had produced from this reaction here, or GTP. At the end of the day, they're structurally very similar. This gives us a total of 25 as the total, and I'm just going to put that in parentheses and say MT for mitochondria, as where I said this was the total for cytoplasm. So 25 can be either one of these things. We can add for just like the grand total, the total energy per glucose, if you want to think about it, can be 25 plus 5, which means that we would have 30, or it could be 25 plus 7, which would be 32 molecules of ATP as the total energy per glucose. Now, this is a theoretical yield. It's theoretical, right? It's never going to actually be that high. Entropy is such a pain in the dick that it makes even the most metabolically efficient machines on the planet, your cells, they can't get 100% perfect yield, right? So it'll never be as high as that. It's always going to be somewhat of lower than that. And one of the things that you also want to consider is that for prokaryotes, they don't really have to deal with this whole movement in and out they are mitochondria, so they don't really have to deal with this whole transfer emotion thing there, and their theoretical yield is arguably kind of higher in certain contexts. But that's it for that. I just kind of wanted to give you an overview because I'm really disappointed we didn't get to go to the electron transport chain.